we're going to start a new topic, even trickier one. Interference and diffraction. So first we're going to talk about interference. Basically, it's about application of the theory we've learned kind of already to light. Well, over hundreds of years, two competing theories have been developing. One theory that light is made of particles, another theory that light actually is a wave. And both theories had pluses and minuses. And for example, it's very easy to explain the development of shadows, the refraction, reflection, if you think of light as particles traveling in all directions. However, there are some phenomena which cannot be easily explained thinking of light as a particle particles traveling in all directions. So, first of all, what do we know about waves? We know about waves that, well, in particular, if you add several waves together, we might have some strange things happening. One of those things is speed, and another of the things is standing waves. Remember a steady wave? Some parts of those waves move, but at some point there is no motion at all. So, at some point, the energy of the wave reaches the possible maximum value. At some point, there is no energy at all. In terms of sound, what does it mean? In terms of sound, it means at some point, the loudness reaches the maximum value. It's as loud as possible. And at some point, there is no sound at all. What would it mean in terms of light? In terms of light, instead of the loudness, we talk about what? How do we describe the presence of light? Intensity, brightness. So, if we could form a standing light wave, that would mean that at some locations we would be observing the brightest light possible. However, at some other locations we wouldn't observe any light at all. No light means what color does it have? Black. There's no color, no light, no color. So in this case, we would have to see something like an arrangement of bright and dark. Well, it would be lines, spots, spheres, or whatever, but a combination of bright and dark things. Well, first, let's try to hear that kind of phenomenon. Again, it's a standing wave, so at least two sources have to be involved in this experiment. A standing wave on the spring, for example, involves what? A source from your hand and a reflected wave, right? So, a second source. A standing wave on the spring. Two ends. A sound wave. Same generator, which means these two sources are in phase, both in phase, same generator. sources have exactly the same magnitude. And the name for two sources like that is coherent. We can easily generate coherent sound waves. The frequency doesn't change with time, no phase difference at all. So, one wave is traveling to you from this source, and another wave is traveling to you from this source. Those waves overlap at some point, and at some point we should observe some kind of a steady wave, but not one-dimensional steady wave, two-dimensional steady wave. So here in this room now, we should theoretically observe some points with very loud sound and some points with no sound at all. So if you could move through the room, you could actually hear how loudness changes. The problem is that would ideally work in the open space. In actual room, we have a lot of reflection, which messes up all the picture. Plus, I don't know, you don't want to walk. So instead of making you walking, I'm going to try to make this source moving. It's kind of relative motion. So if I move it slowly, and if you hear it carefully, you should notice the change in the loudness. It doesn't go completely back to zero, but it should change. I hear some change. All right, do you hear any difference? Yes or no? You have to believe. Well, having two sources at the same place means now there is no two sources. There's only one source, and now there is no two-dimensional steady wave in this room. So if I move two sources together, you shouldn't hear any difference at all. Only when the relative distance between the sources changes, that means sound waves travel different distances to you, and in that case you should hear some difference in loudness. Well, not everybody has a musical hearing, so we can take a look at another example. It's very important to have a visual picture of what might be happening. So here I have a pan with water. You don't see any water. Why? Because the surface is still and light equally getting through all parts of the surface. However, if I poke it, you can see some rain. Why is it happening? Because now there is a wave traveling on the surface, which means at some point liquid getting thinner or thicker than on average. When it's getting thicker or when it's getting thinner, what's happening to the light? It refracts. It refracts away. So, and what you see at front is because light doesn't get completely through that front of the wave. Now, what's going to happen if I have two sources? Well, you could see that here, in this two-dimensional plane, some points were dark, some points at the same time were bright. And now it wasn't just a circle, dark circle. Yeah. Along that circle, we saw some dark and bright spots. There is a better representation of this experiment. Not live, but much easier to see. So this is what one, well, let's try this. So this is one source making waves. Those wave fronts travel away. Now what is happening when I'm adding a second source? That's what's happening. When two waves overlap, well, we call it interference. What kind of interference might happen? We have two kinds of interference, constructive and destructive. So when two fronts both upright interfere, we get the amplification of the displacements, maximum. When two fronts both downright, it's a surface wave travels like this. So in another one, when they overlap like that, they amplify each other, constructive interference. When they overlap like this, again constructive interference. However, if one wave is up and another is down, they cancel each other. How do we call it? Destructive interference. When destructive interference happens, the surface remains flat, so and light getting through. When constructive interference happens, so the thickness is much larger or much smaller, light reflects away, and that's why we don't see light on the screen. So here, well, some examples, mechanical examples of two-dimensional standing wave. The problem with light is we cannot see a light until it reaches some screen. So if I could generate a standing light wave here, we couldn't see it. We need a screen. Well, I have one, and I have well, I don't want to deceive you, I don't have two light sources. I have one light source and a splitter. We'll talk about it in more detail later. So what's happening? So basically one laser beam splits in two, and those two laser beams now interfere like two waves on the surface of the water. And what is happening? If you look, you can clearly see now that here there are bright and dark spots. Well, here in this region, there are places where light, well, travels through, yeah. And there are places where there is no light at all. I will try to make it see for you. I'm not sure. So here, well, it looks like one light ray only. But if you move ahead and ahead, if you close enough, then you can just put it place. Where is it here? Look at it closer. Just go ahead. How many rays do you see? Here, right here. Well, 1, 2, 3, 4, 5 at least, right? So it's not one light ray traveling from the laser. No, it's many of them. And we just need the screen somewhere to see all those rays. Here, thank you. If I could place it, some kind of a screen along, well, very carefully, along all this path, I could see, oh, I still can see first ray, second ray, third ray. This is it. two-dimensional light steady wave. Of course, the question now is, well, how can we actually calculate which place on that screen going to be bright, which place on that screen going to be dark, what it depends upon, you know, mathematical questions. Well, what you need to know, we in this class are going to be considering only 3 cases. So I'm giving you away all the answers right now. What we've seen now is this. It's a double slit or double source pattern. Another situation is a diffraction grating. A diffraction grating looks like this. And pass around. If you look at this, you don't see anything. What actually is in this is 1,000 tiny lines, tiny cuts, 1,000 per each millimeter. So 1,000 per each millimeter, this is like 3 centimeters, 30 millimeters. So 30 millimeters times 1,000, 30,000 lines, 30,000 scratches made here on this plate. But basically, the idea is the same. If you have 2 sources and light interference, if you have 30,000 sources, light definitely should interfere. So we should have some kind of interference pattern for this situation as well. And the third situation we're going to talk about is single slit, single scratch. The pattern looks like this. If you compare these 2 patterns, they both have some kind of a large part similar to each other. But for a double slit pattern, we also have bright and dark fringes inside those large spots. And to calculate the location of a bright or of a dark fringe, dark spot, we have to use specific equations. We'll derive these equations maybe today, maybe on Monday, actually on Tuesday. So this concludes all the future theory, but you can use this to solve your homework problems already. For a double slit, the picture we just see in here, bright spots, bright fringes obey to this condition. D is the distance between the slits or the sources. M is just some natural number. This is the wavelength of the light. And this is the angle between the central of this picture and the specific bright spot. It could be this bright spot number 1, bright spot number 2, and the dark spots obey this condition, saying this is distance between the sources or slits. For my experiment with sound, that would be the distance between the sources, between 2 speakers. In my experiment with the laser, this wheel has 2 tiny cuts, and I have to read, and I can read, can I? So the distance between 2 slits was 1/4 of a millimeter. And that would be this deep. For a diffraction grating, a device which has thousands of slits, you cannot use this expression anymore, because for diffraction grating, if you see, there are no minima. There is central bright spot, and then one more far away on the right, and then another more far away on the left. So use only this expression for the maximum, for the brightness. And for only a thin single cut, thin slit, well, you can use only one equation, which looks like equation for maximum, but it actually describes the location of the minima of the of the dark spots. Well, now you know everything. Now let's just prove that it works. Derive all those equations. So here, our experiment, source number 1, source number 2, that's the distance between the sources. We know that when two waves encounter each other, interfere, two extreme situations might happen: constructive interference or destructive interference. So when two waves travel like that, here we may observe constructive interference or destructive interference. Well, something in between, whatever happening in between, we don't care about that. We care about extremes only. So when constructive interference happens, this one. When destructive interference happens, this one. And here, all we need to know is, well, this is the pattern. This is the pattern for two slits, or two sources. If we could pose it, and if we could place a screen, imagine this is a light wave, so we cannot actually see anything anywhere unless we place a screen. When we place a screen, we would see a bright spot here, a bright spot here, another bright over here, another bright here, another bright here, and we wouldn't see any light here, 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 or here. So the picture, the interference pattern would look like we saw some bright spots divided by some black spots of fringes. A standard interference pattern for a double source or double slit interference situation. What does it depend upon? When we get the maximum, when we get the minimum? Well, all we have to do is we have to calculate the path length difference. So this is one way of traveling to the observer or to a specific location from the first source. This is another way of traveling. And as we know, the result might depend on how they meet each other. That might be one wave, and that might be another wave. Well, in my situation, they cancel each other out. Well, in my picture. What does it depend upon? Well, what's really important is this. This distance is equal to that distance. So imagine that you actually have two waves traveling in opposite directions. Let's say you have one wave traveling like this, and another wave traveling like this. So what does it tell us? First of all, here they both are in phase. That would lead to the maximum intensity of brightness. But more importantly, that would lead to a conclusion that here you must fit an exact number of wavelengths. Well, strictly speaking, it could be no difference at all if the distance is the same, the symmetrical situation like that. So this wave starts like this wave starts like that, then like this, then like this. And of course, here they're going to be in phase automatically. Another situation when there is path length difference, and you can fit exactly one wavelength. In that case, starting from this point again, two waves are going to look exactly identical. So they're going to be in phase again, and again we're going to observe maximum of intensity. Same true if you can fit exactly two wavelengths, or exactly three wavelengths, and four. So as long as inside this path length difference you can fit an exact number of lambda, you always have to observe a maximum of intensity at this location. That's what we call a condition for maximum. The path length difference should be equal to some natural number of lambda. If it's true, at the location where interference happens, you observe the maximum intensity. The minimum of intensity happens when the phase difference equals 180 degrees, they opposite to each other. 180 degrees phase difference equal to a half of a wavelength. So in that case, to observe a minimum of intensity like this, you need to fit, well, either a half of a wavelength, or 3 halves, or 5 halves, or any other odd number of halves. So, to describe this mathematically, that's what you do. This combination always gives you some odd number. Try n equals 1. 1 times 2 is 2, 2 minus 1 is 1, odd number. N equals 2, 2 times 2 is 4, 4 minus 1 is 3, odd number. This combination 10 minus 1 always gives you some odd number. And if you multiply this odd number by a half of a wavelength, and if you can fit this into the path length difference, that means at the location of the observation, you must observe no intensity at all. Completely distracted interference would happen. If you have only one source, it generates spherical waves traveling away from it. If you have another one, well, this Java applet shows slits, not sources. It doesn't really matter at this point. We can assume there is a wave source behind this wall and waves are getting through. But when we make two sources working together, or when wave is traveling through two slits, we can clearly observe some kind of interference pattern, which is the result of overlapping of two waves. This is a standing wave, two-dimensional standing wave. At some places, here, well, there is no sound, there is no light at all. At other places nearby, it might reach some maximum amplitude. It oscillates. And there are also other possible representations of this situation, and you should know because different problems might be involved to different patterns. This one of the patterns, you've seen it, and the pattern which is given, I think, in the homework. Again, we have two sources, and we can play with this. We can change the frequency. Normally, of course, we don't change the medium, which means the speed of wave is the same, speed of sound, speed of light doesn't change. But if you change the frequency, that means you're changing wavelength. If you're changing wavelength, well, the path length difference for different rays might fit down different number of lambdas, and the result depends on that. So, I'll go back, stay here. Okay. So, it is hard to analyze a moving picture if you have a problem like that, I always recommend just make a snapshot of the picture and then just draw everything you want to draw. And that will be something like this. So one source, two sources together might give you different results. Here, for example, well, this particular picture shows you the red spot in the middle, then blue, then red, then blue, then red. So, what does it mean? Red stands for speak, blue stands for throat, and black lines represent no motion and nodes. So here, if you want to analyze a situation like that, you would start from a maximum. Well, this point should be starting from maximum. So red, black. Black means equilibrium. Blue means we go down. The next black means another equilibrium. Then red, again up. So red, black, blue, black, red, black, blue, black, red, black, blue. So we have to end at blue. Blue. Blue means down. Okay? So now we can actually see that this distance, we call it, let's call it R1. R1 fits exactly 2.5 wavelengths. That's the first lambda, the second lambda, and 1/2. That's not the path length difference yet. It's actual length, right? So for this situation of this R1, for this situation, we start from what? We start from a thick, then black, then blue, pink, black, blue, black. Again, pink, black, blue, black. So, alright. Okay. So this looks like this. One wavelength, two wavelength. So this distance, R2 equals 2 lambda. So if you want to calculate the path length difference, what do? You have to subtract delta R is larger minus smaller, 2.5 minus 2, 1/2 of 11. This is the path length difference. So here at this point, what condition is fulfilled for the maximum or for the minimum? For the minimum, right? Because for maximum, the path length difference should be equal to some natural number of lambda, and for the minimum, it should be something like that, an odd number of half, odd number of 0.5 lambda. So this is the case where m equals 1, and we have to use this condition. 2 times 1 is 2, 2 minus 1 is 1, that gives exactly a half of a wavelength. So that's what we call the first minimum. Well, and this first minimum is everywhere along this line. And of course, there's another first minimum here. We always have a complete symmetry between left and right. And that would be the second minimum point equals 2, and that would be the second minimum also. That's how we're supposed to analyze these kind of situations. And if you go to another point, the next point, now R1 equals 3 wavelengths, R2 equals 2 wavelengths, path length difference equals lambda. That's what we call the first maximum here, because it's related to m equals 1. If we want to write the condition for maximum, m times lambda, it equals lambda when m equals 1. This is the first maximum. What about this maximum? How do we call it? It's right in the center of the picture, so we call it a central maximum. It doesn't, well, it's related to m equals 0 value. There is no path length difference between the wave traveling from the first source and the wave traveling from the second source to this point. Or the same matter to this point, or to this point, or to this point. For all these points, the path length difference is 0, and that's why we observe maxima along this line. Now, having said that, why do we see any black region right in here? We just said this line is supposed to represent maxima, and now we say, but there is no light here or no sound. Why? Any suggestion? Because my picture was a snapshot. It's instantaneous distribution of intensity. If you look closely, this point becomes red, black, blue, black, red, black, blue, black. What does it mean? It means at this point, the intensity changes up and down, up and down, up and down. It reaches maximum amplitude, go back to 0, maximum amplitude again. So when we say maximum, we don't mean always. Instantaneous value of intensity at this point would be 0, instantaneous value. When we say maximum, we mean the amplitude of oscillations. The intensity changes. The intensity here is always 0. The intensity here changes between 0 and amplitude. And that's amplitude, well, basically it's equal to 2 individual amplitudes, 2 waves here. When they overlap, first amplitude plus second amplitude, that gives the amplitude of this standing wave at that location. Any questions? It's not a rhetorical question. You can actually ask a question. No such a lot. All right. And it's just another, I've answered this already, so I'm not going to ask you now. But today I am going to ask you at least one first question. Prepare your clickers for this. So here again, along this line, on the perpendicular, we always going to have maximum of intensity. That's the central maximum, and all these points represent the central maximum. And we can use this fact to answer the question about what's going to happen somewhere else. For example, what's going to happen here, here, or here, or here, or here, the easiest way is to look what is happening inside between two sources. So what I did, I took this picture and I enlarged it. So this point represents the source on the left, and this point represents the source on the right. And what we see in between is just a snapshot of red, blue, and black lines. Now, every rule has a disclaimer. When we write the condition for maxima like this, or when we write the condition for minima like that, there is an assumption, very important assumption, which is implied. What kind of assumption is it? We have to say something about the sources. Anyway. What do I show? Yes. Sorry. Sources are not moving, of course, and in phase. When the source on the right emits a wave with the maximum intensity, exactly at the same time the source on the left emits a wave with maximum intensity. In phase, because if it could be different situations, they could be out of phase, or even with some phase shift. In that case, we would have to include that phase shift in those expressions. However, normally, if you read a problem, it tells you sources are in phase. If it doesn't tell you anything, that means sources are in phase. So when two sources are in phase, that means right in the middle between the sources, we always, no matter what, must have what? Maximum or minimum? Okay. This is my question. If you have two sources which are in phase, right in the middle between the sources, at this point, we always will be observing. If you think maximum, think 1. If you think minimum, think 2. Because I will see. So, and 4. Probably this is the most important question for the whole topic, because the rest of the theory or analysis depends on how you understand this. Who doesn't have a clicker? Yours doesn't work? Okay, you should tell me, because I'm waiting for 30, I know. There's 30 people. Okay. Max, very good, thank you. Because when two waves are in phase, that means when they travel exactly the same distance, they will be in phase no matter what. And the distance from this source to the middle point always equals
the distance from the middle, from the second source to the middle point, same distance. There is no path length difference. Always the maximum. They always going to be in phase. So that helps us because now we know, okay, that's supposed to be the maximum. The maximum number what? Is the maximum number 1? Is the maximum number 2? 3? What number is it? 0. That's a central maximum. It starts from 0. When is going to be the first maximum? Well, that's well, this question says, draw transversal representation. So that's probably the easiest way to approach a situation like that. So maximum, minimum, maximum, minimum, maximum, minimum 0, again, and again. Again, this is a snapshot. It is happening now at some instant. And is it possible at some point to have no intensity anywhere? Theoretically, yes, because they move up and down. So at some point, instantaneously, that's how they move. At some point, instantaneously, it would look like a straight line. Why not? And of course, we have exactly the same picture on the left. So 0. What do we call maximum? We call a place with the maximum intensity. Does it matter? Is it positive displacement or negative displacement? No. This is our standing wave between. So let's say you want to analyze what's happening here. What's happening here is exactly the same thing which is happening, okay, here. So when I enlarge the picture, so that's the central maximum, that's the first black fringe, that's the first blue fringe, black, second black, and now this first red, right? So this point corresponds to this line. So this is the distance traveled by the wave from the right source. Let's call it R2. And that's the distance traveled from the left source. Let's call it R1. So if you look at the picture, R2 equals 1 quarter, 2 quarter, 3, 4, 5. 5 quarters. It's usually easier to count quarters to make sure. Yeah. So we start from black, red, black. But each color change equals 1 quarter. 1 quarter, second, third, fourth, fifth. 5 quarters. What about R2? What R1? I usually note R1 the longest out of 2 distances. So again, first quarter, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Correct? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. It equals 13 quarters. Of course, you you know, we don't really care about actual distances. What we care is about the difference. So 13 quarters minus 5 quarters, what does it give us?
13 minus 5 is 8. 8 over 4 is 2.
If I'm mistaken, please correct me.
So the path length difference equals 2 times
Lambda. This is our result. The path length difference, 2 times L. So, M equals 1?
yes or no? Yes or no? Are you alive?
No, M not equal to 1. It's equals 2. We can see it. So, M equals 2 at the second maximum, which is supposed to be the second because that's the central, that's supposed to be the first, that's supposed to be the second. Now, well, now we know everything about two source interference. Because it could be two light sources, two sound sources. You can analyze any pattern like that. Yeah. Here, this point. Well, first of all, the picture already tells you that's supposed to be the minimum. If you want to calculate the pattern difference between waves traveling to this point, it is equal to exactly pattern difference of this point. So, you look at this pattern in the middle, well, between the sources, this is the point of our interest. That's R2, that's R1,
and you can see R2 actually equals 2 quarters, 1, 2. Yeah.
You can, if you know the total distance, that's another option. So this point has R2 equals 2 quarters. If you know the total distance, well, R1 is supposed to be equal to total distance minus R2. And you can now easily calculate the pattern difference and see what does it give you. It's supposed to give you an odd number of pulse of the wavelength. And it's supposed to give you actually which 1, 2, 3, 4, 5, fifth minimum. For the fifth minimum, your expression should look like that. 2 times 5 minus 1. So, you know everything. Well, let's move ahead. This is a practice problem. You can do it at home. This is another practice problem. I want to ask you a question, just one simple question. If you answer that question, you're all set. Path length difference equals 0, 1, 2, 3, 4, or 5. So that's the source number 1, that's the source number 2. This is the location of the observer. Of course, sources are in phase, and two waves traveling. The question, my question to you is, what is the value of path length difference? If you think it's 0, you can press 0. If you think it's 1, you can press 1. If you think it's 5, you can press 5 meters. Okay? I'm switching to as if you know how to calculate, how to find the path length difference. That's it. You know everything. I forgot to announce today, so I'm not going to do it today, but tomorrow, as an experiment, I want to try. So, well, you know, right now, technically, it doesn't matter if your answer is right or wrong. You're still getting the credit. Tomorrow, I'm going to be given full credit for the correct answer, and I have to credit for the wrong answer. Please read the notes. It's just an experiment. See how it goes. All right. That couldn't be 10. You know, just couldn't. That's why I want that experiment tomorrow. Tomorrow is Monday, you know. Right? So this is how far the sound travels from the first source. The distance traveled from the first source equals 4 meters. This is how far the sound travels from the second source. The distance traveled by the sound is 3 meters. The difference equals 4 minus 3, which is 1. Geometrically, if you want to find the path length difference, we have to draw a circle of a radius R2. So this is R2, and that's supposed to be R2. So that's supposed to be delta R. And here we're supposed to fit a natural number of wavelengths if we want to observe constructed interference. For constructed interference, this is the condition we have to use. Now, here, for this situation, my question is yes or no? Yes, 1 or 2. Can n be equal to 0? 1 for yes, 2 for no. If you answered yes, you should rethink your approach. Well, yesterday, on my office hour, one of my old students told me that she was just randomly pressing buttons because she was doing chemistry. It's a physics class, you're supposed to do physics. Well, n equals 0 could work only when R1 equals R2, when there is no path length difference at all. Clearly, here, there is path length difference, so n cannot be equal to 0 in this problem. So the smallest value of L for the maximum is 1. And other possible value for n to observe the constructed interference is 2, 3, etc., etc. If we want to, well, you know, these speakers connected to a generator. You remember that little box. So we can tune up the frequency. We can tune up the wavelength. By tuning up the wavelength, we can make this person doesn't hear any sound. In that case, we should make the wavelength equal to specific value, which would fulfill the condition for the maxima. And for maxima, we can start counting from 1 or 2, etc., etc. Now, the textbook gives you a different version of this equation. In the textbook, this equation has plus, not a minus. So in the textbook, it starts from 0. I'm too old to change the way I've been taught. This is how I've been taught. This is an actually more intuitively comprehensive equation, I think, because there is no central minimum. There is a central maximum, but minima start counting from 1, 1, 2, 3, 4. And now, well, we can calculate everything. So the pattern difference is 1 meter. That means for different n equals 1 gives the first wavelength, which gives the maximum. N equals 2 gives the second possible wavelength, which gives the maximum. And also, if we apply the condition for minima, n equals 1, n equals 2, n equals 3, will give you frequencies and wavelengths for completely destructive interference at that location. Well, there are more possible problems. You can practice at home. This is the question I want to ask you. We're not going to do any calculations, but what's going to happen, do you think, if we immerse the whole system in different media? Well, the most important question, what is happening to the wavelength? So that's what I'm going to ask you. We know that to observe a maximum or to observe a minimum, one of these conditions has to be fulfilled. So it's about wavelength, right? So there's a wavelength for the sound in the air. What is happening to the wavelength when we immerse the whole system, well, including this poor guy, into the water? So your possible answers are wavelength goes up, doesn't change, or goes down. What is happening to the wavelength? The sound when we immerse it into the water. All right, okay. All right. Well, I guess everybody answered, so. We kind of divided almost evenly. Well, that's an important question about the wavelength, because sound behaves in the opposite way as the light behaves, and we're going to talk about light very soon. So for the sound, well, frequency. First of all, what doesn't change? Frequency. The period of the wave, the frequency is related to the source. So these speakers connected to the same generator, it's still making the same number of pulses per second. So frequency and period don't change. But if the speed of the wave goes up, and in a water, speed of the sound is higher, that means the wavelength also goes up. And you can calculate the new wavelength and apply conditions for minima and maxima and figure out what's going to be happening. I think, if I remember correctly, it should be a minimum now. For the light, the situation is different. In vacuum, light travels with the speed of light in vacuum, fastest speed possible. But in the medium, in a glass, for example, or in the water, the wavelength actually goes down because the speed of the light goes down. And the new wavelength in a medium is the wavelength of the light in vacuum divided by index of refraction. And if you calculate this new wavelength, you can apply again condition for minimum or condition for maximum, figure out what's going to be happening. Well, but the only difference between sound waves and light waves is that, well, first of all, conditions for minima and maxima for light the same as for sound, no difference at all. There is one additional condition. Here, the wavelength of light is so tiny, so relative to any regular distances, it's almost zero. So if you deal with light, the rays, light rays, could be considered as parallel to each other. And this is the larger version of this picture. And when all these light rays travel from the source, from the laser to the screen, practically parallel to each other, we can add one more equation, strictly geometrical. So this ray reaches the screen traveling a little bit longer distance. This is supposed to be the path length difference between this ray and that ray. So how can we calculate the path length difference? We can use the right triangle rule. The path length difference is going to be equal to the distance between the sources times, well, the sine of this angle. This equation will not work for sound waves. For sound waves, if you have two speakers, the wavelength is about 1 meter, yeah? And the distance is about 1 meter. That will not be a right triangle like that. But for light rays, since this distance is very small and this distance is huge, yeah, this technically is supposed to be an arc of a circle. However, we can think of it as a straight line that gives a right triangle, and we can add one more condition. And as a result, so the condition for maxima for bright spots is the same as it was for sound waves. The condition for minima for dark spots is the same again. But now we added one more condition. And that condition relates also the distance from, well, this slit to the screen. So now, if we combine these conditions with this geometrical equation, this what we get for light for bright spots, this what we get for light for dark fringes, dark spots. Well, here's just a illustration based on our wave representation of sound waves. If we place a screen here, that's what we see: central maximum, minimum, first maximum, second minimum, etc., etc. So on a screen, well, the difference between this theoretical prediction and actual picture is that here we are assuming we're dealing with two sources, two light sources. In actual experiment, we're using two slits. The difference is that, here. For two sources, the intensity of light kind of evenly spread around. So the intensity of the picture along the screen, on the screen, is supposed to be the same. Actual picture is slightly different. When we have two slits, the intensity is different in different directions. And in that case, the picture kind of dies out. And tomorrow, we actually will calculate the locations of these points, these spots, where minima disappear. Well, our equations for the double slit interference, or double source interference, like this, tell us at which angle we will be observing a dark fringe, at which angle we will be observing a bright fringe. So right here in the middle, we have the central maximum. Central maximum, first minimum, first maximum, second minimum, second maximum, what's it going to be? Third maximum, third minimum, fourth maximum, fourth minimum, etc., 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 etc. We just use different m's, plug it in this equation. For the central maximum, m is 0, that means angle is 0. That is the rate for the central maximum. For the first maximum, we plug in this m equals 1, and we calculate the angle from the central line to the first maximum. Then plug in 2, and we calculate the angle between the central line and the ray, generating, producing, providing the second maximum, etc., etc. Same for minimum. Now there are many questions related to what will be happening to the picture if we make some change. What changes can we make? We can bring closer or further away from the screen. We can change the distance between the slits. See? I have a variable slit. When I move this wheel, clockwise or counterclockwise, I'm changing the distance between the slits. Now, you see the pattern getting wider. Now, the pattern shrinks. Does it tell you what is happening to this distance? What do we need to do to make it wider? Do we have to make the slits closer or further? Just take a look at this equation. It tells you everything. Basically, everything is based on this ratio. If you make this ratio larger by increasing wavelength or decreasing distance between the slits. If you make this larger, that means the same maximum number 1 or 2 or 3 will be reached at larger angle. So if you make this ratio larger, your pattern should be wider. Like that. If you make this ratio smaller, for example, by increasing the distance between the slits, your pattern should shrink. What about distance? Well, it's easy. So this is the situation number 1. That's a central line, the first minimum or maximum. What is happening to the pattern if we move the screen closer? 1 minute. If we move the screen closer, we do not change the angles between the rays. We do not make any changes with the wavelength, or we do not make any changes with the distance between the slits. We just change the location of the screen. If we move it closer, new. Maxima and minima also will be closer to each other. If you move the screen farther away, then the pattern is getting wider. And to describe this mathematically, all we have to say is that one more second. For, let's say, maximum number m, we can introduce this distance from the central spot to the mth maximum. And in that case, this ratio, this distance divided by the distance to the screen is supposed to be equal to the tangent of this angle. It's a pure geometry. And for a double slit situation, you see these angles are so small, 5, 6 degrees, no more. So we will almost always can make an assumption, which is true for small angles. Almost always we can replace sine with the value of this angle, as well as tangent with the value of that angle. However, we must calculate the angle in radians. This is the first question I want to ask you. What's going to happen? And we change the wavelength. So this is a pictorial representation of interference pattern generated by two sources, light sources, sound sources, doesn't really matter. Today, I want to remind you, we're on an experiment. To get a full credit for this question, you're supposed to answer it correctly. An incorrect answer gives you a half. If you're not here in the classroom, that gives you 0. And let's see if I scared you enough. One day I might run a test like that in a classroom with flickers. Why not? You don't like that idea, no? One more respond supposed to be entered. Your filter still doesn't work. You're supposed to buy new batteries. Okay, so in that case we can stop. All right. Answer 2 is the most popular answer. And what is happening? Wavelength goes down. That means this angle is supposed to decrease as well. If we decrease the angle, we're supposed to shrink the pattern. So getting closer is the right answer. Congratulations to 82% of the class. This is just an explanation. Now, next. That's what we would see actually if I had this kind of experiment with red or violet lasers. For a red laser, we would see bright or dark fringes farther apart from each other. Shorter wavelength, patterns shrink. Shrink. Now, next question. So, same situation, however, the variable we change now is the distance between the sources.
I'm gonna stop collecting response. If you're still waiting, stop me. And okay, now we have some division in your answers. Answer number 1 is the most popular, and that is the correct answer. Because if you look at this expression, when the distance between the sources in molar, we are decreasing the denominator of this fraction, so the whole value of this fraction is supposed to be increasing. That means the angle getting larger, the picture is supposed to be wider, so they move apart. Well, that's mathematical explanation. Now we are moving the screen. So what is happening? The distance between the sources and the screen is increased. So we are moving the screen away from the sources. Okay? Then, so whoever answers all questions correctly gets a time. Gets a time. Anyone? I guess that's it. Interesting. Today I have 10 less people than yesterday. Why? Where is? All right, you know your answer, and I can look inside the system and figure out. So here, if you look at this equation, the tricky part is there is no distance in that equation. So, but to answer this question, you just need to think about what is happening to bright fringes on the screen. Let's say this is, well, this is the central maximum, that's the first maximum, this is another first maximum, and this is the distance between maxima. And if you move the screen away, the distance between the maxima gets larger. So again, get farther apart. Now, sometimes to answer a question like that, oh, here, okay. There is another interesting and convenient variable, which is the spacing between the fringes. This is how we could use this variable to answer the previous question. So this is the central maximum for m equals 0. This is the distance from the central maximum to the maximum number m. And we call it usually y sub m. And that's the distance from the central maximum to the previous maximum. So if we calculate this difference, this is how far two consecutive bright fringes apart from each other. And calculation, that's a nice exercise, will give you this result, well, for small angles. So now this expression explicitly has this variable in it, and that also helps to figure out what is happening when you change it. When the distance L between the screen and slits increases, the distance between the slits, not slits, the distance between the fringes increases. So they move apart from each other. Well, that's what we would see, and actually we saw yesterday when I was moving the wheel. We increase the distance, we increase the size, the width of the tether. And one more question. Now we take this whole apparatus and we immerse it into water. So it was the air around it, now it's in water. What do you think is going to happen with the tether? Okay? Let's try again. Okay. Minus 1, 25, 24, one more. Okay. Can I stop? Already screen. Answer number 2 is correct because, well, when you're changing the medium, you're changing the wavelength. And for the light, the wavelength always goes down. The new wavelength in the medium equals the wavelength in the vacuum divided by the index of refraction of the medium. And n is always greater than 1. So in the medium, lambda is always smaller than in the vacuum. You decrease this variable, you decrease the angle, you decrease the spacing between the fringes, so the pattern shrinks. Any questions? These are basically all kind of possible questions and answers for any optical device. It could be double slit, double source, single slit, grating. Well, what's going to happen if we alternate one path length by placing some transparent medium? Well, it's not a question, but what is happening inside this plastic or glass? We just said the wavelength changes, and when the wavelength changes, now these two sources are going to be out of phase. And when two sources or two slits are out of phase, what does it mean? The distance, the angle doesn't change, but the picture shifts. So here, right in the middle of this screen, we might not observe the maximum anymore. That maximum might be shifted. Well, the problem with the light is that it's very, very hard to make two light sources being coherent. It's very easy for sound sources, two speakers connected to the same generator, coherent. Same frequency, same phase, but if you take two bulbs, it doesn't work for light anymore. Even if you use two different lasers, you have to tune up very carefully to make them coherent. So it's much easier using one single source and to divide, to split the light from that source into different parts. So now these two sub-sources would be coherent. So that was the original idea to test the wave nature of light. Because, well, if you had those two holes and this particle traveling through two holes, you wouldn't see any interference pattern on the screen. You would see only one spot hit by the particles and another spot hit by the particles. That's it. So when Thomas Young, he was actually a physician, and well, physics people didn't like him very much, because at that time the Newton's theory of light was kind of dominating. But this experiment actually eventually proved that light is a wave. And the theory for double slit situation is exactly the same as for double source situation. Same conditions, everything is the same. And the only difference is the pattern looks slightly differently. And today we'll learn why the difference is happening soon. This is a typical problem related to a double slit or double source situation. Well, double slit situation has a name, Young's experiment, Thomas Young's experiment. You have a light traveling through two slits, and here on the screen you observe a sequence of bright and dark fringes. And depending on what we know, we can find everything we need. For example, here in this problem, what we know is how far the slits are apart, and we know how far the screen is away, and what we're looking for is this. How far is the third bright fringe from the central maximum? Well, the central maximum is in the middle of the screen, because in this situation, Young's experiment, these two sources always are in phase. So we just have to plug in numbers and calculate. Well, first we can calculate this angle. Since it's a maximum, we have to use the expression for the maximum number m. M is 3, the wavelength is given, the distance is given, you know the angle, the rest is geometry. This is a right triangle. For the right triangle, if you know this distance and the angle, you can calculate this distance. That's it. This is 0.95 of degrees. So if you would want to calculate this angle in radians, what would you do? Anyway, what is the conversion factor between degrees and radians? Yes. So the conversion factor, well, degrees equals pi radians. So if you want to calculate this angle in radians, this is your proportion. So this angle in radians would be, well, pi times 0.951 over 180. This is a really, really small angle in radians divided by 180. Yeah? So for this situation, the sine of this angle and the tangent of this angle would be equal to the value of this angle. So technically your solution is much easier. You can just take off these functions. You just need to use radians. And in that case, you don't even need a calculator, basically. Okay? A little trick. But that works only for double source situation, double slit situation, and we'll see soon a single slit situation. It doesn't work for diffraction grating, because for diffraction grating, angles are large. Well, adding sources. Now we're going to talk about diffraction grating. What if we have 3, 4, 5 dozen, millions of sources? How would it affect the interference pattern? Well, this question is not going to be graded. So it's just testing your intuition. All right, what do you think? And should be more, should be stronger. Got it. Two more. This one. No, this one. All right, I have a picture. Well, first of all, the right answer is no. As long as we have more sources than 2, we cannot use condition for minimum. When do 2 waves cancel each other out? When they're out of phase. And when 2 waves are out of phase, yes, completely distracted interference is happening. However, if you add in the 3rd wave, that's it. The 3rd wave messes picture up. So even if 2 waves cancel each other out, the 3rd doesn't. So it's really, really hard to make wave all 3 or 4 or 5, even more waves, to make them cancel out completely. So when you're adding sources, you cannot use anymore the condition for minimum. But condition for maximum remains, So, because if you're adding more and more sources, the direction for maximum stays the same. It doesn't affect the angle at which each maximum is seen on the screen. So, when you're adding sources, you still can use this condition. These angles still will give you the locations for bright fringes or bright spots. However, for situation where you have several slits, you see, the intensity of the light kind of changes in a way. So the location of the maximum doesn't change, but each maximum kind of getting more and more narrow. And basically there is no minimum. There's just a wide range on the screen with no light at all. Let's see. So this is just a laser beam, one single one. And this is, you saw it, a diffraction grating, which has 1,000 slits per millimeter, so about 30,000 cuts. Honestly, it works like 30,000 light sources. And, well, see, there's now an additional spot above the central point, and there's one more here on the bottom. And we actually can look at the beams traveling away. The central one which goes to the first maximum up, and one which goes to the first maximum down. Light splits. We see maximum, central maximum, first maximum, maybe sometimes depending on the wavelength and the grating and distance, second, third, but in between we just don't see any light at all. That's how diffraction grating works. So we still can use a condition for maxima to calculate the location of each maximum, which is the same condition we use for Young's experiment. But the condition for minima doesn't work anymore. Just forget about it when you deal with 3 or more sources. And now, as I said, you saw one beam was traveling right here, and second right there. The angle between the light beams was like 45 degrees. It's not a small angle. For a situation like that, you cannot use any approximations. You have to use exact functions, sine, tangent, and you have to use a calculator. Or if you know that your angle is convenient, like 30 degrees, 45 degrees, you know the values for those angles. Sine of 45 is square root over 2. Tangent of 45 is 1. And this is my next question. What if I have a diffraction grating and I have light with different wavelengths traveling through it? Well, in my question, I have 2 laser pointers. The green one and the red one. So, no diffraction grating. This is what we see, 2 spots. If I place a diffraction grating and light will be traveling through, which picture actually going to be on the screen? The first one, the second one, the third one? Prepare one laser. The green one, and actually I have a blue one. Twenty-six, 27, well, more people. Okay. Number 3. Let's see. Well, that is correct answer. Because if you're increasing the wavelength, the angle is supposed to be larger. So let's take a look. So what I have is, let's start from red and green. Red and green. The hardest part is to keep them together. Come on. Don't die. And oops. Yeah. So the central maximum is here. I'm placing red. Sorry. Okay. Nice. Here, you can see the first maximum. The green one is somewhere here, and the red one is far away. What if I take green and blue one? Okay. Green and blue. We just have shorter wavelength, the blue one. So now the blue the first maximum of the blue should be closer to the central spot. And yeah, if you look here in this region, that's what we see. That's the central. Now we can see the first. For the blue, for the green. What if we take, oops. What if we take a white light? Well, white light has all possible colors, right? So we should see a rainbow, the spectrum. If you look on our left, or actually on the right as well, you can see the spectrum. And it starts from blue and goes to red. The blue is deflected the least, the red is deflected the most. And that is true for all possible optical devices. Double slit, diffraction grating, and we'll see it works for single slit as well. So, this is an example of a calculation involving higher orders of maximum. First, second, third, fourth. What is happening? Well, we just, here in this part, we're comparing the allocation of the maximum for 3 different colors: red, green, blue. So, the straightforward calculation gives that for the first maximum for the blue, that's supposed to be the value of the sine. Well, inverse sine gives the angle, etc., etc. And we can draw a correspondent line for each of these maximum. First red maximum, second red maximum, third red maximum. First blue maximum, second, third, fourth. So why does blue light has 4 maxima, but red only 3? Because just again, straightforward calculation eventually gives you the value for the sine greater than 1, which is impossible. If you plug in the numbers, 2020 divided 2200 divided by 2000, it's number greater than 1. So for each wavelength, there is always the last m for the maximum. As long as the sine starts being greater than 1, that's it, it's impossible. And also we can see that sometimes, well, orders mix up each other. So if you look at this picture, it's really hard to say at first which line represents which order. Well, you have to start from the central one. Central is always white because all colors mix up together. And that would be the third maximum, the maximum of third order for the green light. This line represents what? Again, 1, 2, 3. The maximum of the third order for the blue light. Well, now, as we know, a wave diffracts. Diffraction is a property of a wave to bend about edges. So here, if you have a relatively large slit or obstacle, relatively large, what does it mean? It means relative to the wavelength. The wavelength is small, the size of the slit is large. What we observe is basically, we would say, it's kind of a shadow. Yes. If this was light, we would see on the screen a bright spot here and no light at all here. here or there. So in this situation, light behaves like particles. What is happening if we actually making this opening smaller and smaller? We can observe more and more bending behind. Eventually, a slit like that starts acting like a point source. Plus, in addition to this situation, sometimes some waves from the edges of this opening also overlap and interfere. And here on the screen we can observe, again, bright and dark fringes, bright and dark spots. So we call this situation diffraction, and we need to figure out how to, for example, how to calculate the location of dark spots on the screen. Well, historically, the experiment was not with opening. The experiment was with an obstacle. So if you place something, some object in a way of particles, you observe a shadow behind it. However, the wave theory tells us that if we place an obstacle relatively small, in that case, because of bending behind this obstacle, we would supposed to observe actually a bright spot right in the middle of that shadow. And historically, that experiment was very dramatic because, again, French Academy of Science was listening to a physicist who was kind of trying to prove this theory, and Poisson, which was a famous physicist, said, "No, it can't work because we would see a bright spot in the middle." And they said, "Okay, let's do it," And they did it, and they saw something like that. Basically, what they did, they took just a small object. Well, what we did it here in this room, we actually used a small steel ball laser pointer. It takes a while to adjust it, so but that's the result. You can actually see a bright spot in the middle. That proves that light actually is a wave. Well, but to actually merge different properties of light, wave properties of light and particle properties of light, we can use the so-called Huygens principle. Light is a wave, so wave has a wavefront, and each point of a wavefront could be seen as a point source which generates spherical waves, and those spherical waves interfere, and that's how they form a new front, and a new front, and that's how the wavefront is moving. So as long as the wavelength of light is much smaller than any objects around, we always can forget about wavefronts. We can represent the light in terms of beams, rays, which are perpendicular to fronts. However, as long as the wavelength is of similar size with objects, openings, obstacles, in that case, the wave nature of light is very important. And so the difference between these situations, same light, same screen, the width of this slit is different. When it's really wide, that means wavelength is really small relative to the width. When it's really narrow, in that case, interference pattern is formed on the screen. How? This is how. What's important is, for a single slit situation, now there is no equation for maxima. So, two slits or two sources, two equations. One slit one equation. Many slits, again one equation. But for a single slit, now we cannot find the location of maxima, we can find the location of minima, dark fringes, dark spots. This illustration tells you why. So, well, of course, light, when traveling through the opening, travels in all directions. This is one specific direction. Let's say this is specific angle at which we can fit exactly one wavelength in this path length difference. This is path length difference between this ray and that ray. Well, these two rays are in phase. We would have to say they amplify each other, right? So kind of it should be a maximum. However, that's not true. Because, well, first of all, there's also a middle ray, which is twice more intense, which twice more intense than either of these. It doesn't have any edge close to it. And this ray is out of phase with this or that. So this ray cancels those two. Cancellation means disruptive interference. Okay, but these three are not only rays traveling away from this opening, but we can compare, well, this lower half of this slit and this higher half of this slit. For each ray here, from here, we always have exactly one ray in the top half, which cancels it out. You see? They out of phase. So we have set of rays which cancel each other completely out. This happens when we fit exactly one wavelength in this distance. Or, of course, exactly 2 or 3 or 4. So as long as the angle between the central line and that direction satisfies this condition, this is the width of the slit. This condition is basically, again, the application of a right triangle. The hypotenuse, the angle, we calculate in this side of the triangle, hypotenuse times the sine of the angle, and as long as we can fit a natural, an exact, an integer number of wavelengths, that direction represents the direction of the complete cancellation of light, of the minimum. So, one slit, one equation, however, now is an equation for the minimum. And the picture would look like this. The difference between one slit interference and two slit interference is very important. That's a single slit. One narrow cut. And that's what we see. A very wide, bright spot right in the middle. There is no equation for this bright spot. The equation is for this first dark fringe. That's the first minimum, that's the second minimum, that's the third. You should be closer probably to see it, but in the lab next week you'll see it. Again, that's the first minimum, second minimum, the third. That's what we call the central spot. What we can calculate the angle which gives the first minimum. We can calculate the angle which gives the second minimum. We can calculate the distance between these two spots, which would give you the width of this bright spot. We could calculate the distance between these two dark fringes, which would give the width of this central spot. If you look at the double slit interference pattern, again, we have a wide, bright spot in the middle. However, we also have dark fringes inside that. Yeah. So the two interference pattern kind of similar. However, for this situation, for the double slit interference pattern, well, that would be this very spot in the middle, right, would be the central maximum. And that would be the first maximum, the third maximum, fourth, fifth, and that would be the first minimum, second minimum, third, fourth. That's how we count it. And the relationship between these two patterns is very interesting. Well, again, the pattern has the limited size because the sign cannot be greater than 1. So this is what we would observe for double source interference. This is what we observe for single slit interference. Minimum number 1, minimum number 2, and light between the minima. Well, double slit pattern seems like a combination of these two. We just take this shape and we use it as an envelope for this one. What does it remind us? It reminds us bees. Sound bees, you know, wow, 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 wow. But now we have bees in space, not in time. Because this envelope modulates the double source pattern, and that's what we see. When the minimum of the single slit pattern coincides with the maximum of a double source pattern, we get missing maximum. It disappears. And then it goes, some light goes back again. So, well, it could be n equals 2 or 3, but normally for a single slit, we don't see a very wide picture. So this minimum kills this maximum. So that's why double slit pattern doesn't have the maximum where double source pattern would have it. And we can compare, we can relate the distance between the slits and the width of each individual slit now using these two patterns together. Basically what we say is that, well, let's say this is a screen. So here, for this particular spot, this angle is supposed to be the same in both equations. That should be this angle which describes the first minimum of the single slit interference pattern. However, at the same time, that should be the angle which would describe this. Well, in my example, what is it? 1, 2, 3, 4, 5, the fifth maximum of the double source interference pattern. Since the angle is the same, we can derive this expression which relates this number, the width of individual slit, and the distance between the slits. And for many situations, this is the first minimum. So when m equals 1, that's how we can relate these variables. And before we leave, this is an example of, just 1 second. Come on, yeah. This is an example of this kind of calculation. You can use this expression to calculate that width. It's going to be the distance between the slits, and well, this is m equals 1.